Hi everyone, welcome back to Experimental Math. This week we have Amita, Malik talking to us about parity of restricted partitions.
Thanks, Anna. Thanks for being here. I'll talk about parity results. Restricted partitions. So before we start, let's write the definition of partitions. So partitions of an integer into parts from a set A is defined as, so you take any positive integer A and you say that a partition lambda of n into parts in your set A. So over here A is some subset of natural numbers. This is a decreasing sequence, finite sequence of positive integers, say lambda 1 and so on. I don't know. Is equal to lambda m, and all these lambda j's are in your set A for 3 equal to m and so on to f, where n written as lambda 1 plus lambda 2 and so on plus lambda m. So what one is usually interested in, the number of ways you can write this n as some of these lambdas. So p sub a n is defined to be number of partitions of n where these parts in your set A. So this sub A denotes where your parts are coming from. Example, if you take A to be the whole set of natural numbers, then this is usually denoted as P of n, and this is the usual partition function that we have. For example, if you take n equal to 5, or let's take small 3, small, and then there are how many partitions? 3, and you can also write it as 2 plus 1, and you can also write it as 1 plus 1 plus 1. You shouldn't get confused that because there is 3, you have exactly 3 partitions. It's not true that Pn is equal to n. In fact, this function, when a is actually equal to n, this function grows exponentially as n grows. Okay, so now let's take more particular sets. So if you choose A to be, let's say, set of squares. So n squares such that n belongs to integers. Then if you take n to be equal to 3, then now you are not allowed to use this 3 as a partition. So earlier you had 3, 2 plus 1 and 1 plus 1 as partitions, but now each of your parts has to be a square. So this is not good, this is not good, only this is good. So in that case, P sub A of 3 is equal to 1, while in this case, P sub 3 was equal to 2. Okay? values which are even half the time. So Pn is even approximately half the time. Half the time. What we mean by this is, i.e. more precisely, if you take any n, capital N, and look at the limit of the ratio of all n, little n larger than 1 and smaller than this, such that P of n is even, and you divide this by n, so you are talking about the ratio, then this limit is 1/2. So it's even half the time and it's odd half the time. Now what is known about this? This belief or conjecture is far, far wide open. The first result in this direction was by Holberg in 1959, and he showed that En is even, and similar result for Pn to be odd, infinitely odd. So before that, we did not even know that this function actually takes even values infinitely often. So he showed that this is true for even as well as odd values. Okay, so now what is known is even or odd in fact about square root times. So more precisely what we are saying is that if you just count these numbers, this numerator, then you get that this is larger than square root of n. For this limit to be equal to 1/2, you have to show that this is 1/2 times n, and we only are able to show that it's about square root of n with some log factors. Okay, and instead of writing all these results, I'll just say that results in this direction are given by many people, many mathematicians from A to Z, Aldrin, Roosevelt, Chawla, then we have Bono, lastly we have Ada, and the rescue, to name a few. So in case I miss some name, this is just because I wanted to make it look like A, B, C, D up to Z. So this is what we have. Now, what can you say if you take restricted partitions where your parts come from set A? Is it still true that you get this ratio to be 1/2, or is it even still true that this function now will take even or odd value infinitely often? And that's the purpose of this talk. So we consider partitions coming from the set A, which I define now. So for fixed positive integers, K, little a and b, consider a set A, which depends on K and AB, to be the set of all kth powers of integers such that your m is actually in the arithmetic progression a mod b. So m is congruent to a mod. So what you are doing is you are fixing an arithmetic progression a mod b And in that arithmetic progression, you are taking kth powers. And your parts have to be these numbers. Okay, so let's look at these examples. So, in particular, when you take A to be 2, A and B to be 1, then what you are saying is that you are interested in partitions with parts coming from the set which has squares of natural numbers, because A and B are equal to 1. So in that case, your A to 1 comma 1 is same as the set of n squared, such that n is this, and that's exactly this example that we considered. Okay, in particular now you can take not just squares but also squares of odd numbers, for example, because odd would just mean that you are taking A to be equal to 1 and B to be equal to 2. So then your this is the set consisting of odd squares. Okay, so as an example, for n equal to 5, the usual partitions Pn is given by 5, 4 plus 1, 3 plus 2, 2 plus 2 plus 1, 2 plus 1 plus 1, and plus 1, and 1 5 times. Okay, so out of these, now we want squares which are odd. So 5 is not a square. This goes away. 4 is a square, 1 is a square, so this is good. 3 is not a square, 2 is not a square. We don't even need to look at 2 because the first itself is not good. This is gone again, this is gone again, and you are left with only 2 partitions.
Odd squares, right?
Oh yeah, okay, we are taking odd square, yes, thank you. So this is also odd. Because 4 is a square, 1 is odd. Yes, it's not this example. Thanks. So now from these many, what you are left with is only two of them. So P of A sub 2 equal 2 of 5 is exactly 2. So now all your function, all the values of your partition function get just sort of very different from the usual partition function that you saw.
1, right? It's 1.
Oh, again I did now. Thank you.
Can I ask something?
I'm glad I'm not doing any counting today.
Sorry, can I ask something just in general about this all kind of questions? So all these results that you gave A to Z, do they all talk about parity?
Yes.
So, I mean, why is parity a natural thing to ask, or is it just a difficult thing to ask?
So if you take n to be larger, there are some congruences known for, let's say, mod 5, mod 7, and so on. For just 2, it's usually not that easy to use, for example, modular forms to say something about the parity. And for those, for other numbers, let's say for 5 and so on, they have been result in that direction. But for 2, it's not known. And 2 is more natural because you just want to know how often is it even odd.
Yeah, okay, just even basic behavior is strange, that's what you say.
Yes. Okay, so now we ask similar question for these partitions. So it's enough when you want to study these partitions with general A and B, it's enough to take sets where A and B are co-prime. Because if this is not co-prime and you have D larger than 1, so D is a GCD, if it's larger than 1, then for any n such that D to to the power k does not, d to the power k which does not divide n, you know that p sub k, p of a sub k a comma b of n has to be equal to 0, because you can just factor out d to the power k from each of these parts. That means that has to divide the right hand side, which is the sum of the parts, and hence it has to divide this. But if this is not true, then you already know that this is 0. There's not much to do. And if it divides n, then okay, p of a sub k of n is same as, if it divides this, then same as, just factor out d to the power k from all your partitions. So the number of partition doesn't change. So this is in fact same as p sub a k a comma b of n over d to the power k if d to the power k divides n. So it is enough to study only those A's, only those sets for which A and B is A and B are co-prime to each other. So they have GCD prime. Okay.
So, sorry, I guess I'm missing the last step, which is if you know that P of n is 0 for all of these n, how does that solve the question of the asymptotic number of evens?
So this is not for every n. So you will have numbers, you will have n's for which d to the power k does divide n. So there are, now you want to know how often this is true, for how many n's this is true, and for how many n's this is true. And from here you could see that, okay, there are many numbers for which d to the power k does not divide n. If there are infinitely many, then you are already done. But over here, what can you say? Like, is it still infinite? Because over here, this could be, all of them could be actually odd in number. Or they could be all even, and in that case, modulo 2, they are all 0. So then you are not saying, or you are not able to prove that this function also takes odd values infinitely often. For that you need to do some work. Okay, so there is the conjecture in this setting also. This is in joint work with Bruce Bent and Zaharescu, and we say that for fixed A, B natural numbers such that A and B are co-prime, then this is still true. If you take the limit as n goes to infinity of number of 1 less than n such that pk p a sub k equal b of n is even again about half the time, with one exception, exactly one exception. When k is 1, a is also 1, so k equal to a equal to 1, and b is equal to 2. So that means when you partition your set into odd integers, odd positive integers, then this ratio is not 1/2. And this we saw from experiments. So I will show you the table towards the end of the talk. And once we saw this in the table, we were like, oh, there's something special going on over here. And we were actually, this was quite easy to show that in that case, this is not 1/2, and we have exact asymptotic for that. Okay, so let's move on. I'll just say that in this exceptional case, we are able to show that if you take all those n's for which, so this is when k is 1, k is 1, k is 2, this is odd, this is about square root of n. Okay, so this is odd very, quite a few times, not too much. Even in these cases, this is expected that this should be about n over 2, but in this case, it's way too smaller than n over 2. This is in fact just asymptotic to n, and that is proof uses, I won't really give the proof, but use Euler's theorems and Euler's theorem for the usual partitions, that number of partitions into all integers is same as the number of partitions into distinct parts, and the pentagonal, Euler's pentagonal number 3. And you get this straight away. So this should be square root of. Alright, so now we move on to this case, when it's not an exception. What can we say? Can we say that they are odd infinitely often, for example? So this is again result with Bruce and Zaharescu. And we say that if you, in your case, with notations, let's see, earlier notations, P of A sub k, A of B, n as even and odd infinitely often. And this is true even in this exceptional case, because this is still square root of n, so as n goes to infinity, we still get this. So when we prove this, in the proof we don't really see this exception. We see this exception only when we do the experiments and actually see how often it's even odd. So this proof is uniform, doesn't matter what your exception is over here. So I will give the outline of the proof of this. I really like this proof, but I also want to say that if you generally it's not easy because of congruences that you can come up with something as quantitative as, like, for example, Canono and Scott Elgren showed that this is for the usual partition functions, they are about square root of n or log of n. So if you drop the condition that you are in a congruence and you just consider the parts which are kth powers, so in this case I am setting A and B to be equal to 1, so I am only looking at partitions with parts into kth powers. In that case, we are able to get quantitative results for this partition. So what I am saying is that if you take n between capital 1 and n such that P of A sub k 1 1, so I am partition into kth powers. This is odd not just infinitely often, but you can do contour. It's 1 minus c over log 1 of n, where your c is some number larger than log 4. And I want to say that over here, k is larger than 1. This is very important because this k is exactly equal to 1 when we are talking about partitions into just ordinary partitions, and for that our proof does not work because then this will actually improve a lot on those previously known results, and the reason why it fails is because this mk involves zeta k, the Riemann zeta function evaluated at k, and when k is equal to 1, we know that zeta grows up. It has a pole at s equal to 1. So in that case, you have too much over here. And how we get zeta k in the proof is, in order to get these bounds, you have to do some k-free integers counting. So all those integers which are k-free in the sense they do not have kth powers in their prime factorization. So k-free integers counting, and that involves zeta k. That's how we get this. Okay, so maybe towards the end I will tell you how we get this. To start with, I want to show this result. Any question? Okay, so idea of the proof of, let's say, this here. So start with the generating function of your partition function. So I'm just going to write this notation instead of a sub k a b. I'll just call it a, because my k and a b are fixed. So this is, and the generating function of this is, so we found these partitions with 2 to the power n going from 0 to infinity. The partition of 0 is 1. We just say that this is equal to 1. And this is given by product 1 minus q to the power n, and all those n which belong to your set A. So you are multiplying all those, when you actually multiply it out, you will be adding in the power of q all those n's for which you have, these are members of the set A. So now consider your function, this generating function, but write it as a formal function, formal variable x, so that you can differentiate, you can do some analysis on it that you want to do. So define this to be product of exactly this, x m and m is in your set A. Okay? And now you take logarithmic derivative. So this is defined formally. Logarithmic derivative. That means what I am doing is I am taking the derivative of log of f of x, and that's given by log of this product. Okay, so on the left hand side you get f prime x over f of x. I can write this product as sum of logs, and that is which one? Here n this, and I'm just opening the power series extension for logs. So n is from 1 to infinity, x to the power mn divided by n, right? But I need to differentiate this. So this was just this log of this product that's given by a sum of log of 1 minus x to the power m, that you get this. Now in order to differentiate this, you just write mn over here and you get minus 1 over here. And now n gets cancelled. And now in order to make this power nice looking, I'll just multiply by x both sides. So what I get is this. This is equal to sum over mn a, I can write m over here and x to the power n because of this. Okay, so now because this is formal power series, I can assume that my x is really small and all this is absolutely convergent, and I can change the order of summation. Then what we get is, let's call this L over here, so x to the power n is L. What inside you are left with is summation m, but m belongs to A, where this L was written as m times something, so that just means that your m belongs to A, but m also divides L. And once you have that, once you have this, now you can get some results over here. So this is important part. Summation m belongs to L. So this reminds you, if we take A to be the set of natural numbers, this is just the sum of the divisors of L, right? So now this is sum of divisors of n, L, divisors of L from set A. So your divisors have to belong to set A. Okay. So if I can just multiply by f of x both sides, then I get x f prime x equal to f of x, and this right hand side becomes summation. There is a notation for this. So I will say this is defined as sigma of, you are adding divisors of L, but because your parts come from set A, we will just denote it by sigma A. And when we have that, then what I'm left with is a power series sigma L x to the power L, L going from 1 to infinity. Okay, so now this is nice equation, you have power series both sides, and let me call this as h of x. So this is the crucial part. Up to here, the proof of this theorem start, and this is the same. And after this, we want to study h of x, and in order to get quantitative results like in this theorem, you need to study hx in a fine way than we did it over there. Where we wanted to show that there are infinitely many values where it's take odd number. So this is equal to just f of x. So, okay. So now this is where all the math happens. So we will switch to now studying the function sigma sub A of L. So there are two propositions, let's say one proposition, one lemma, and both of them are interesting in their own right. They can be modified for a different partition. Let's say if you choose a different set A, then if you can modify those propositions accordingly, then you can get similar results on infinitely often being odd and even. So let me write down those. So, and how do we arrive at those propositions is what I start with. So now your claim is that, so I'll do it only for odd. It's easier to do it for odd, but turns out to be more complicated for even. So I want to do that for the sake of time. So our claim is that P sub n odd infinity of. Okay, so proof is suppose not. So therefore you should be able to find only finitely many integers, and let's order them n r, such that only for n equal to nj and j going from 1 to r, you have that f of x, which was summation t sub a n x to the power n going from 0 to infinity. Now this is congruent to x sub n to the power j going from 1 to r, because only for n equal to nj you get this to be odd. So for all others this is 0, and if it's odd then it's same as saying it's 1 modulo 2. So I can get rid of the coefficient here, and you get this finite sum now. So your generating function is this finite sum now. And now put that in that equation over here. Let me just name it 1. So use this in 1 to get summation. I'll just so you have this x and j, because I'm differentiating f. So I get nj minus 1, j going from 1 to r. And now this x gets cancelled with this x in the denominator, so I can just cancel this. On the right hand side, you will get just f of x, which is this, times h of x, which was sigma sub a n x to the power n goes from 1 to 1. So this is just putting, substituting the generating function in our equation.
Isn't that just congruent?
Yes, that's correct. Sorry, thanks. Okay, so this is mod 2. If I don't write, congruence is always mod 2. Okay, so now if I can show, let me write this proposition. So the heart of the proof lies in showing this proposition, which is about this sigma a. So if I can show that for any fixed positive integer n, there exists an odd integer L which depends on b, satisfying that it's the value of the function, the sigma function at b is 1. So this is odd, or it's congruent to 1 mod 2, and it's even after this, up to a chain up to this b. So this is even for j starting from 1 to b. Because b was arbitrary, what you are claiming is that for any integer, or however long you want, however large integer you have, you can always find some other integer such that the value, sum of the divisors with coming from this set A is always odd, and after that, if you count the number of divisors from set A, this is always even, and this can be as long as you want. And once you have this, let me just complete the proof. So for now, assume that this proposition is true. By proposition, you can choose your b to be largest number that you had over here, n r. Therefore, there should be some integer. Let's call it n sub n r, which is odd, such that sigma a of n of n sub r is odd. So this is 1 mod 2, and sigma a of n sub n r plus j is congruent to 0 mod 2, and j is from 1 to n of r. And once you see that, you look at this again and you compare the coefficients of some large power of x, so that over here you get 0 because the power is large enough, and this side, because of this condition on sigma, you are able to show that this is odd. So you can't have even and odd. A number which is odd and even at the same time, and that's a contradiction. So let me just write that. All right. Okay, so now you compare coefficients of, let's call this 2 coefficients of x to the power n sub r, n sub n plus r plus n sub r. So large enough so that you do not have a coefficient over here. In fact, so this is, I have to add L and R because L is positive, this is positive integer, and that's NR is the highest one that you have over here, highest power. So this on the left hand side gives me that you get 0 congruential summation. So what you have is sigma sub A of L, and I want my power of x to be this. How can I get that power to be this? If my, so n was going from 1 to infinity to start with, and x to the power L, that means L should be same as nj. So I should say, okay, this becomes finite sum, so let me just write j equal to 1 to r. Okay, I'm just changing the notation. K from 1 to r, sigma L, and nk plus L should be equal to L sub nr plus nr. Okay, so my power x to the power n is equal to this only if I get n to the power k from this side. I have 2 on this side. Yeah, so n to the power k plus l, that's my power over here, nj plus l. That is same as ln to the this, nr plus l. So once you have this, that means you already have value of r over, value of n over here. So k going from 1 to r, and I can replace my l by this value. So sigma A of L is given by L sub nr plus nr minus this number. Right? And now you are done because you know that when k is equal to r, so that means nr minus nr, you get just 0, and you are talking about, oh, I got 2 somewhere. Why did I write 2 sums? Okay, so then I know that sigma of A of L and R is odd, and for all the other ones, because now this number is larger than equal to 0 and smaller than equal to, in fact, smaller than equal to B, which is NR in our case, right? At the max it can be n sub r, because all these nks are positive. Okay, so that means this is equal to, or I should say congruent again, this is congruent to exactly sigma A of when you get k equal to r, so this, and that's congruent. So this is my proposition, and this is congruent to 1 mod 2, but that's not true. We started with 0 on the left hand side. So that's a contradiction. Okay, so now if you can prove this proposition, you are done, right? Similarly, you can show that this is infinitely, it's even infinitely often, but I won't do that here. In order to show this proposition, let me just write what other lemma that we use. So now, enough to, so therefore enough to prove this proposition considering the time I have, I will only use this board. And the lemma, the way we prove is, or using the lemma, the way we prove the proposition is quite interesting. I won't be able to show this, but we have to construct some primes, and the way we construct is these primes is by induction, and by that you have, after that you have to raise some congruence, and that's done using Hensel's lemma that we all know. And once you are done with that, you can use Chinese remainder theorem to conclude the proof. So let me state the lemma. So let C be an odd integer, a positive, and because we are talking about this set, so everything is, all these propositions are specifically for this set. And suppose there exist Q primes Qj satisfying this. That Qj is larger than equal to b plus 1. Again, we have this any fixed integer capital B. So all your primes should be at least b, should be larger than b, and you should be able to come up with some Lj, some numbers corresponding to each of these primes, such that once you raise it to the power n, you get 1 mod. So this is same as saying that Qj, each of these primes are co-prime to b, because if that's true, then you have inverse of this function, so there is an order. That means after raising it to some power, you will get 1 mod b for sure. So this is same as saying that Qj is co-prime to b. And you also have, so this is 1, 2, and if you raise C to 2k, you get this congruence. This is congruent to 0 mod Qj to the power k to Lj minus 1. However, if you change power of Qj over here, this is no longer true, and so this is not 0 mod these primes Qj with power 2 of this, so twice of this, 2 Lj minus 1, and this is for j going from 1 to b.
What's Lj?
Lj? Lj is, so you should be able to find some Lj.
Oh, there exists an Lj.
Yeah, there exists Lj. And that they will exist if I can replace this condition by, so this is IP, that each of Qj is co-prime to B. Because if this is true, then you can find this. Okay, once you have all these conditions, then sigma A of C to the power k, 2k is odd, and sigma A of C to the power 2k plus j is even for j going from 1 to. Okay, and if you have this, so what, in order to prove your proposition, if you can construct, so you can always take C to be the number that you wanted over there. So C to be what did I have? C to the, so LB to be C to the power k. We wanted this to be L sub B. So now, so this is so enough to construct these primes, right? Construct these primes or satisfying these primes to prove the proposition. Since C to the bottom. Okay, so in order to, I will not prove this, but in order to prove the proposition, we need to construct these primes, and we do that inductively. Over here, I won't go into the detail, but this is exactly where we have to use use Hensel's lemma to come up with these primes, because we want these congruences modulo with higher power. Okay, I think I'll stop.
All right, let's thank our speaker. Are there questions?
Yeah, I can ask some. So I guess the 50s proof of congruent is so he couldn't give quantitative results, right?
I think he just decided to give the infinity one because the paper is really short. It's like 2-page thing. I don't even try it or anything. And because this is a very nice combinatorics thing, so after this, after results of Kohlberg, there are quite a few results known for, just to show that there are infinitely many such.
But Kohlberg could not have done this because the zeta at 1 would explode, you say, right?
So you won't get this strong strong bound for the usual partition function.
But you can still use the age and whatever. You can still do the same initial construction, but not work out the exact asymptotic?
Yes.
That's what you said?
Yeah. So similar results are known. Instead of n to the power 1 minus c or log it, you have 1 minus 1, n to the power 1 minus 1 half. That's like square root of n.
Yeah.
And also with some factors of log. And those are the best known results that we have for the usual partition functions. And that, in fact, those bounds are also, they also have several proofs. Some of them are using modular forms, some of them are using, in fact, functional equations in the Riemann beta function and the theory of L functions. That's a paper by Bruce Min, Zariski, and Azari.
So those other proofs maybe can be used to approach other sets A, right? And
Yes.
this kind of proof works for this.
Yes.
Yes.
Because the way we do this is just by analyzing this series that I call h of x, this one. So basically sigma of n. And if you can find the density of this, like how often this is odd even, you can get bounds like this. So you need to study this kind of function. So you could apply to partitions. In fact, I think more or less the same proof goes through for partitions into the plane partitions. And probably you could do something like this for partitions into primes, but that's what I'm looking at currently. Can't say for sure that it works.
Yeah,
But
it's probably pretty different.
yeah, because primes, suddenly the nature changes, but if you have some other functions, for example, partitions into different colors, that can be done using this technique.
Are there other questions? No, let's thank our speaker again.
Partitioning into a smaller set. So
Yeah, we can talk later.
should we start?
Yeah.
Okay. So in this table here, we count the number of even and odd values of selected partitions. So in this row, k is always equal to 1. But for example, if you take a to be 4, b to be 5, that means we are talking about partitions into parts which are congruent to 4 mod 5. And over there you see that it's so close. The even values out of 100,000, 49,668 of them are even and these many are odd. So you see that percentage wise this is 49.6, 50.3. Over here there is one which is really close. There. Okay. 2, 3, 4 as you see in the middle. When k is 2, b is a is 3, b is 4, you have 50,001. There is exactly one more n for which the function takes even values, and this is 49999. So it gets really close. And we are only looking at n up to 100,000. So as you increase n, you do see that they do really get really close to each other. And if you look at the table carefully, you see that in the second row, there is something interesting happening. So this is the case, exceptional case that I talked about here. Case 1, A's 1 to B's 2, so you are partitioning into odd parts. It's even most of the time. And odd 516 times out of this 100,000 values. So you might feel that, okay, maybe it's going to 0, but it's not going to 0, it's going to infinity, as we show that it's of the order square root of n, but it's going really, really slowly in comparison to the even ones. So from this table...
Were you brave enough to come up with the correct asymptotics and try to do this?
So for the part, I give very brief outline of the proof. It was just using Euler's theorem and Euler's pentagonal theorem. It's very easy to show.
What is the what is the correct asymptotics for this special case?
So it's odd about square root of n times.
It's square root.
Square root
That's
of
what you
n.
said. Okay.
Yeah. So this case we could show, and this just came from the table as we saw the experiment. We were like, oh, what's happening over here? And then, okay, let's look at its generating function. And then we saw, okay, this is actually good. Okay, I'll stop here. Thank you.